Okay, we're going to solve the following linear ordinary differential equation using the Wronskian method of solution. Now, equation 1 here, which is x squared y double prime minus x y prime plus y equals 0, is actually a Cauchy-Euler equation. And it is linear because the coefficients, which are variable, um, are only variable in x, not y, or any of its derivatives. Okay, so let's just highlight a few other things. This is a second order ordinary differential equation, which means that there are actually two solutions, y1 and y2. I'll just write them here like this. If this had been a third order ordinary differential equation, then we would have had another solution, y3, and if it had been fourth order, we'd have had an additional solution, y4, and so on. So an nth order differential equation has n solutions. This is second order, so it only has two. Now, I'm going to keep these here because, first of all, if you're someone who's studying exam questions or questions out of a book, you might actually be given the first solution. I'm just going to erase that because it was a little bit skew-if. So you might actually be given the first solution, which in this case actually is Cx. And that actually is a solution of this equation. We're actually going to start from the very, very beginning and actually show that y1 is equal to cx, because we're assuming that we don't have any of our previous techniques to solve a Cauchy-Euler equation using the more standard methods, because there are standard methods to solve such an equation. We've got to assume that we don't have those and we only have the Wronskian, and so we have to use the Wronskian to work out what both y1 and y2 are, and hence the whole general solution. So I've sort of given you this solution here, y1 equals cx. By the way, y1, you can just write this as y equals cx, because the reason why it's solution is that when you substitute y equals cx and both of its derivatives, so the first derivative and the second derivative, into equation 1, you should find, and in fact you will find in this particular case, that the left-hand side here is actually equal to 0. But we're actually going to show that because, of course, we can't be sure. And we need to know that if this term here, y equals cx, is a solution, then equation 1 should be equal to whatever is on the right-hand side. So what we say is that if this solution, I'm actually going to call it equation 2, if equation 2 is a solution to equation 1, then it actually solves equation 1. It solves it exactly, and you get whatever is on the right-hand side. Now, usually in examination questions, you might be given this term here, y equals cx, and be expected to then use whatever techniques are at your disposal to find y2 and thereby find the general solution. But in this particular case, we're asked to use the Wronskian method, which is something we're going to go on to now. So first of all, there's kind of two Wronskian techniques we can use, and actually we combine them. The second one I'm going to use is a kind of determinant, a Wronskian determinant. But before we go on to finding the determinant of equation 1, we're going to use I'm going to write it down here before we go into the next stage. We're actually going to use W equals W0 e to the minus P dx. But before I explain this, which I'll call equation 3, let's make that a little bit clearer. 3, right, before I explain what each of these terms actually are, I'm going to rearrange this equation, x squared y double prime minus x y prime plus y equals 0, to get it into a form that is actually easier to manage and easier to solve. And actually, you need to do this when dealing with these kinds of linear ordinary differential equations where the coefficients are variable. So actually, if we divide equation 1 by x squared, that's this term here, we get a coefficient of 1 in front of the y double prime, and that's really what we want. Even if this were 2 or 5 or 77, it doesn't matter what it was, we want to divide, excuse me, we would want to divide by whatever this term is here to get a coefficient of 1 in front of the y double prime. And that's very important. You must do that. So what we get, if we divide by y squared, we get y double dash minus 1 over x y prime. So we've got y double prime minus 1 over x, y prime plus y over x squared, and that's equal to 0, and we're going to call that equation 4. Okie dokie. Right, now let's go back to the Wronskian. I've stated the Wronskian here, but I'm going to use this Wronskian to try and guess a solution. And when we've got that solution, we then need to substitute it back into equation 4 or equation 1, it doesn't really matter which, to see if it is a solution for reasons I've already given, that we want to see if this side here is equal to 0. So I'm going to guess a solution. I'm going to suggest that the solution is y equal to just some constant times e to the minus p dx. Right, okie dokie. What is p? Well, we've got equation. Let me see. Let me just go up a little bit. Right, so we've got these two expressions. We've got expression 3 and expression 4. How can we relate the p here to equation 4 or whatever is in equation 4? Well, it turns out that the p is actually this term here, minus 1 over x. So if we just go back to the solution, we have y equals, in fact, I'll actually write it up here. It saves a little bit of space. So we've got c e to the minus integral of minus 1 divided by x dx. And I hope you can see that a little bit there. So what we have is y equals c e to the integral of 1 over x, which is the same as x to the minus 1, times, oops, let's just make that a little clearer. So we've got 1 over x dx. And of course, I'm sure you will have identified that this is equal to c e to the, whoops, let's just delete that. And we've got e to the power log of x. Okie doke. What is ce to the log of x? Well, any exponential to the power of a logarithm of a number is quite simply just this number, x. So this becomes y equals c, let's get that right, ce to the, in fact, actually, I've gone a little bit ahead of myself there. That is just ce. So that is just cx. There we are. So we've got it. Well, we think we've got a solution, but do we know that the solution we were originally given, y equals cx, is indeed a solution to this equation? Well, let's try and find out, because what we have to do is to prove that y equals cx is a solution, we have to find the first and the second derivatives of this and substitute everything, including the original y, back into that to see if we get 0 on the left hand side, therefore being the same as what is on the right hand side. So this part of the equation on the left hand side has to be equal to 0 on the right. Okie doke. Right, so if we differentiate this, we've got y prime equal to c, and we've got y double prime equal to 0. If you differentiate constant, you get 0. Right, okay, so I'm actually going to write this equation out again. And of course, we can actually use this equation here. It doesn't matter whether we use equation 4 or equation 1 to show that y equals cx is a solution. So I'm going to use the simplest one. So I'm going to use equation 1. So we've got, let me see, there we are. We've got x, let's make that a bit better, x squared. I'm actually going to write the full equation out again. Minus x y prime plus y. Well, we know that it's equal to 0. We want to show that it really is. So if we substitute, I'm going to use a different color here. If we substitute the y equals, let's start again. If we substitute the y equals cx in, the y prime equals c, and the y double prime equals 0 in, we can soon find out what we get. So we've got x squared times 0. I'm actually going to put a multiplication sign in there because we don't want to make it look like a function or anything. So we've got x times 0 minus x times y prime, and I'm going to have to look at that, which is c. So we've got x times c plus, let me have a look, cx, and what is that equal to? Right, well, I'm sure you can do the mathematics. So we've got minus cx plus cx, and that is simply equal to 0. So yes, we seem to have shown that the left-hand side of equation 1 or equation 4 is equal to 0. So therefore, y equals, I'm actually going to write it like y equals y1. Y is ultimately going to be the general solution, but the first linearly independent solution is equal to cx. So we've established that that is a linearly independent solution. Now, how do we go forward from there and work out y2? So what we do is we use the determinant form of the Wronskian. So if we use w equals the determinant of, let me get that straighter. So let me see, there we are. So we've got the first entry, y1, that is our first linearly independent solution here. So it's this linearly independent solution, y1, which is cx. But we'll come to that in a moment. And then we've got y2, which we don't know. And what we have to do is we have to differentiate y1 and y2. So these are the entries of that matrix determinant. Let's put y2 there. Right, okay. So we know that y1 is let me see, I'm not doing very well here, am I? So we've got y1, which is cx. We don't know y2, but we do know what y1 prime is because it's just the derivative of this first entry here, which is c. Make that look a little more convincing. So there we are. Let's just get that right. C, and y2 just becomes y2 prime. Okay. So what do we do now? Well, we have to find the determinants of that, but what do we do beyond finding the determinants? Well, you might remember that earlier on, I actually said that Wronskian was equal to w equals w0 times the exponential of the negative integral of p dx. Let's get rid of, sorry. So there we are. We we want to get rid of that green splodge. So this is Wronskian. W equals W sub 0 e to the minus of the integral of p dx. And we're going to use that in the part that we're now looking at. So perhaps I'm taking the cart before the horse here, but I'm going to write down that W equals just some constant. This would normally be your W sub 0, e to the minus p dx. But this we know from finding the first linearly independent solution is c e to the power of, well, it turns out to be 1 over x dx, because p is still exactly the same. It's still minus 1 over x. And so we know that that is equal to, I'm actually going to give this a different subscript. We're going to call this C2. C2x. So the Wronskian has both a determinant form and it's also equal to that C2x term. So if we work out the Wronskian, well, how do we do that? So let's go to line green. Okay, so the determinant of the Wronskian is Cx times y2 prime minus C times y2. So we have here Cx times y2 prime minus, let's find this is clearer, cy2, and we know that the Wronskian is also equal to this c2x, c2x. So we'll just equate that c2x and we can simplify the expression. So it turns out if you simplify this by dividing through by cx, we get dy2 over dx. Make that look like a bit more of a convincing d, and that one as well, minus 1 over x y2 equal to c3 just on its own. Now c3 is, we'll just write it over here, c3 equals c2 over c. So I've just simplified that a bit. So we've got a nice ordinary differential equation. How do we solve that? Well, we need an integrating factor. So the integrating factor is equal to e. It's a bit like finding the Wronskian, really. It's e to the power of this. I don't know where my where my pen has gone up there, but anyway, I hope nothing terrible happens. So this is our indicial part of the exponential. So we've got e to the minus 1, well, actually it's e to the minus integral of 1 over x I'm actually going to delete that and make it a little bit more clear. Right. So let's just erase this C3, these C3 terms, because it's getting in the way a little bit too much. So we've got e to the power of the integral of minus 1 over x dx. Right, okay. So there we are, minus 1 over x, and we've substituted that in to the initial part of the exponential. And if you work that out, you've got e to the logarithm of 1 over x, simply because minus 1 over x is just minus the log of x, and you can manipulate that to get the log of 1 over x, and e to the power of a log, right, there we are, is equal to just 1 over x. Right, now I think what I ought to be doing is labeling some of these additional equations. So we've got equation 4 up there, and we've come all the way down to this equation here. So I'm going to call this equation, is it 5? Have I, oops. So 5, yeah, so we've got equation 5 there. Right, so if we multiply 1 over x by equation 5, we get 1 over x dy2 by dx, and we've got minus 1 over x squared times y2, and that is equal to C3 over x. Right, so we've actually simplified our situation, and we can proceed to solve this equation now. So what we have here is actually the derivative of a product. So we've got d by dx of 1 over x y2, and that is equal to what is on the right hand side, which is C3 over x, and if we integrate both sides, we have 1 over x y2 equal to C, what's the daisy? We've got C2 times the integral of 1 over x, and of course that's plus a constant, we'll call that C4, and so we have 1 over x y2 equals C2 log of x plus C4. And we're pretty much getting to where we want to be with this. So if we multiply both sides by x, we get y2 equals C2 x log x plus C4x. Oops, I'm making my usual mistakes. Do watch out for my mistakes. So we have that. So we have a second linearly independent solution. Right, so this is our second linearly independent solution. I'll make that less skew-if. How do we find the general solution? Well, we know that y1 is cx. Well, I mean, I gave you it here, but we did work it out. Let's see where that is. So we've got y equals cx, and we've got y1 equals cx and y2 equals c2x log x plus c4x. Therefore, y equals y1 plus y2. The second order differential equation, so we add the two solutions together. So we've got y equals cx plus, and I'm going to write this slightly differently. I'm going to write the c4x first. C4x plus, and I think we've got C3, well, we've got we've got C2 log x. If I haven't made any mistakes, it doesn't really matter what you call your constants, but obviously it's good to be consistent. C2x log x. Well, you will notice that in this equation, these two terms are pretty much similar, and you can actually, well, to be quite honest, you can take out the x factor. So you've got c plus c4 times x plus c2 x log x. Okie doke. Right, well, we've basically found the general solution, because all we need to do is put some constant equal to c plus c4. You might have met this sort of thing before, where one of the linearly independent solutions becomes kind of absorbed into the other linearly independent solution, and that often happens with these kind of problems. So we've got y equal, I do want to make that look a little more clear. So we've got y equals a times x. What have we got here? Plus, we'll call that c2 a b, plus bx log x. I'm going to put brackets around that just so it makes it a bit clearer. Or does it? Maybe I shouldn't. Sometimes some mathematicians put modulus signs around the x, but anyway, you can just leave it like that, I suppose, and you can do the analysis to see what the solution actually looks like. But that is our general solution to equation 1. So we'll just write down, it implies general solution. General solution. And so that is that. And I hope that you tune in to my next presentation, and also that has been some help. And I look forward to seeing you then. Okay.